Hello. In this video, I'll make use of this Colorado applet to talk about the three states of matter: solid, liquid, and gas. So this is the solid state. In solids, the atoms or molecules are usually very close together. At such separations, the intermolecular forces are very strong. So strong that every atom or molecule has a fixed position in a very rigid lattice. It's like together they decide to lock one another up. So the result, a solid has a fixed volume and shape. This is the liquid state. In liquids, the atoms or molecules are usually not that close together. And at such separations, the intermolecular forces are only strong enough to keep everyone together as a whole. But it's not strong enough to prevent individual atoms or molecules to continuously glide from one neighbor to another. This is why a liquid cannot stand on its own, Instead, a liquid always flows down to fill the shape of a container. The result, a liquid has a fixed volume but no fixed shape. This is the gaseous state. There is zero intermolecular forces in a gas. The atoms or molecules just act like billiard balls zipping around in straight lines until they hit something. This is why a gas always expands to fill any container. A gas has no fixed volume and no fixed shape. So how does a substance transform from one state to another? Let's use H2O as an example. So this is ice, This is ice. So let's heat it up. Let's raise the temperature. Now, do you see the jiggling? As it gets hotter, it will jiggle more vigorously. So that's what temperature is about. We have this mental picture that more vigorously they jiggle, the hotter it is. Heat it up, heat it up. It has melted, right? The water has melted. So notice one thing. There's something special about water. So most things, when they melt, they will expand, right? So this is solid, this is liquid. There's always more space among the liquid molecules compared to when they are solid. But the water is quite special. This is ice. When it's ice, there's a lot of space between the H2O molecules. But when it's liquid, it shrinks. This is why ice floats on water. Do you notice this guy? That's called evaporation. You see, all these atoms actually have a range of energy. As they interact with one another, they exchange energy. So some people, if they're lucky, they get more energetic. If you're unlucky, you lose some energy. So if you happen to be on the surface, and if you happen to be energetic when you're on the surface, then there's a chance that you can break free from the rest of the H2O molecules, and that's called evaporation. The rate of evaporation will be higher if it's hotter, so let's try to raise the temperature a bit. Okay, and let's wait for somebody to break free. Anyone? Oh, yep, that guy, this guy is just broken free. Yep, that's evaporation. So among the liquid atoms, surely some of them will be more energetic than the others, and those are the ones, if they happen to be on the surface, they are able to break free, and that's called evaporation. This is different from boiling. To boil, you need everyone to be vibrating so vigorously that everyone is actually ready to break free. So we'll heat it up, and then boom, that's boiling. So yes, boil, all these are water vapor now. Now, since we are here, I might as well highlight something. So this is gaseous neon, this is gaseous oxygen, this is gaseous water. Do you notice any difference? There's something striking about the motion of the oxygen and H2O molecules, right, as compared to neon atoms. So if you are not monoatomic, then you're actually capable of rotational motion. If you are monoatomic, then of course all you can do is move around, right? You are not able to do any rotation. So because of this, oxygen molecules, for example, will have both translational Ke and rotational Ke. And this can explain why diatomic gases have higher heat capacity than monoatomic gases. That's because if you are diatomic, when you supply thermal energy to a diatomic gas, some of the energy must go into increasing the rotational Ke. So not everything goes into increasing the translational Ke. And that means the temperature doesn't go up as much for the same input of thermal energy. So the kinetic theory of matter basically says that everything is made out of atoms. And with just this very simple idea, we can actually explain a lot of things that's happening around us. Alright, that's all. Ta-ta!